So you've probably heard the terms TCP and UDP before. Maybe you've even made jokes about UDP, like, I can tell you, but I'm not sure if you're listening. Ha 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 ha. Or, maybe I have a joke about UDP, but you might not get it. Ha 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 ha. So, if it's so funny and UDP so unreliable that we make jokes about it, why is UDP becoming the dominant protocol on the internet? With essentially every real-time application now switching or always using UDP, modern web browsing even is making the move from TCP to modern HTTP3 over, well, UDP. So is UDP actually as unreliable as the jokes seem? Is TCP actually that much better? Does TCP introduce new problems that are causing us to swing back in the UDP direction? And was a protocol designed in 2000 that would have fixed all of these issues if it wouldn't have been for NAT, network address translation? So if you're interested in a bit of a deep dive on transport layer protocols, UDP, TCP, and the stream control transmission protocol, then come along on this adventure. Before we dive too deep into the transport layer protocols and how they work, I think we need a bit of a refresher on the OSI protocol model and where the transport layer fits in relation to applications and the network layer. So, time for Professor Applard. So in a sense, the goal of network engineering is making sure that two applications can speak to each other no matter where they're located. So we have web browser and web server, chat clients, etc. They need to exchange application data, and the network needs to provide services for them to do so. So you've probably seen the OSI model before. It looks like this. This was actually designed by committee. Actually, two different committees collaborated to design this. So it is sort of the worst possible thing you could come up with, most complicated, most feature creep, etc. And that's why normally we shrink it down to just 5 layers. So the data layer, the link layer, the network layer, transport layer, application layer. So I'm also going to ignore the bottom 2 layers for this talk, and we're mostly just going to talk about the network layer and the transport layer. So the network layer's goal is to connect 2 hosts together. So I have 2 hosts, they might be servers, they might be clients, whatever they are. They need to speak to each other across the vast network of the internet. And that is the job of the network layer, to get packets to the correct address. So just like sending mail through the postal system, you have a physical address, that's where you're physically located. The computer has an IP address, that is where it is logically located on the network. It's within a subnet, sort of like a street address, etc. And the network layer can route packets across the world to get them to the correct host. But one host is not one application, so we might have a bunch of applications. So we need some sort of multiplexing, and that is what the transport layer does. So the transport layer, broadly, specifically addresses an application within the host. It might do more than that, but that's the bare minimum for a transport layer protocol, is to address the specific application. And the bare minimum transport layer protocol we have is the user datagram protocol, UDP. So let's take a look at how an application might work using UDP and see what sort of challenges it might face. So welcome to Applard's Transport Lab, I guess. So here I've got a little mini PC. It's connected over wired Ethernet and also Wi-Fi, and I have a different IP address on both sides so I can test that connection. I could have done this in like a purely virtual environment, but the packet loss there is essentially 0. So over Wi-Fi, we'll see things like a little bit of packet loss and packet reordering. So I thought that was nice to demonstrate. So I want to build some sort of chat app because I think that'd be a good demonstration of UDP. So essentially, you send messages. Each chat message is one UDP packet. Pretty straightforward demonstration, I guess. So let's see how that looks here. So I'm just going to get the receiver started. So we're just going to receive on port 666, and we're just listening there for anything that comes our way. Okay, so now our sender's sending messages. So we have like a message number here, and the actual text of the message coming through. I didn't want to type out like a million messages to test this, so I'm just using the script of the B movie here as an example. Each line is one message. And so they're flying by, and if any of them are out of order, it'll print them in red. And we haven't had that problem yet, thankfully, but we're only about a third of the way through the movie, so let's speed up a little bit. So here at the end, it says that we didn't lose a single message. We had exactly the right number, and we had exactly the right number of bytes, and they were all in order, so we didn't lose anything. So despite UDP's reputation for losing packets, on this Ethernet network sending about 100 packets per second, which is really not a lot. We didn't lose a single one, and we didn't reorder a single one. So maybe we should go a little bit faster. What do you think? So over here on the sender, I'm going to change it to use Wi-Fi instead. And also I sped it up to do 1,000 packets per second. And we're going much faster this time. And again, 100% successful. So I guess we'll bump the packet delay up to, I don't know, 10 microseconds. This time we got 3 out of order, but we didn't lose any. So UDP doesn't really guarantee us really anything. So UDP in its header provides port numbers so we can multiplex different applications based on their port number. And that's essentially it. So I've had these two applications agree to use port 666. And other than that, UDP is just providing a single message transported across the network and demultiplexed per application. So it's not guaranteeing that I'm going to receive the packet. It's not guaranteeing that I'm going to receive it in order. What it is guaranteeing is if the packet is malformed, it'll be dropped because it has a checksum. So if a packet would have been mangled, we just lose the whole packet instead, which I think is a reasonable trade-off. So here we happen to receive almost all our packets in order, and all of them happen to receive intact. But maybe if I make it even faster, then we'll start losing some. So now we're going to try with no delay at all. There we go. Now we got a lot of loss. So we just got the first half, and then we just lost everything else. So this is what happens when we run out of buffer space. So since I just dumped 7,000 packets in the network stack, it only had enough buffer space for, looks like, 2048 of them. So it just discarded the rest. And that can happen if you're not careful about rate limiting yourself to what the network can actually support. So UDP doesn't do that either. If you try to send too many packets than the network can support, it just drops the rest because it doesn't have space. And this is done at the network layer. And so TCP and other protocols will try to rectify this by only sending as much as the network can handle. So that's another feature that UDP lacks. So if all we had to work with was UDP, we could make applications reliable by having them track the messages they send, resend them, etc. But that puts the whole burden for that algorithm onto the application. And most importantly, it puts it on every single application separately. So way back in the 70s, the ARPANET engineers realized that they had a whole bunch of applications that were sending data and needed reliability. The network at that point, they had tried reliable, they had tried unreliable, they preferred the unreliable at the network layer, and so they decided to write the transport control program for the what would become the transport layer. And this essentially provided reliable transmission similar to what they would get by connecting a teletype over a modem, but guaranteeing there were no errors there. And so TCP gives us a few more guarantees than UDP did. So it does multiplexing, multiple applications on the same host sharing the same host address, but different transport addresses. So I have port numbers. It also gives us a connection establishment. So we establish a connection between the two sides over which we exchange data. And we can track if that connection has been broken, if it's established, etc. So it's a bit more high level than just sending individual messages. The third thing it guarantees is reliable data. So it guarantees that all of our messages will make it to the end or the connection will close. So if it can't make it, it drops the connection, but most of the time it's guaranteeing that our data has made it to the end. And the last thing it guarantees, the data makes it in order. So we can't swap the order of any data. It has to come strictly in the order we wanted to send it. So those are the guarantees we get with TCP. So the reason for moving this functionality from every application into the transport layer, TCP, is that essentially every application needs these guarantees most of the time. So since the transport layer is implemented by the operating system, we can share that bit of code for every single network socket we create, instead of rewriting reliable data transmission code in every single network application. So over here in the transport lab, I have modified my example chat application to work over TCP instead of UDP. It was not quite as trivial. So TCP sends bytes in order, not messages. So in UDP, we were guaranteed that if our message was small, we could fit it in a single UDP message. That could be bigger than one IP packet, so we can go up to a couple thousand bytes in a single message. And so if we fit our messages in that size, we guarantee that the message boundaries remain intact. My example, that was every chat message. And with TCP, we're guaranteed that each byte is in order, but we're not guaranteed any sort of markers on when a message starts and ends. So what I did is I added some extra bytes that tell me how long the next message is. So first I read the length, then I read that number of bytes, and that gives me one message. So I wrote this little receiver helper that keeps querying over and over until it gets the number of bytes it wants, because TCP will read one single byte at a time if we ask it to, or possibly less, or etc. And then down here we read 2 bytes to get the size, and then we read that many bytes to get the packet. So again, we'll start the receiver, and just like that, we got all of our bytes. 100% successful, 100% in order, even on Wi-Fi, even at high speed. So TCP guaranteed what it said it would. But that strict guarantee gives us a couple downsides. So what if, for example, we're having a nice chat, and then you're like, dude, I took this cool video today while I was out on a hike in the forest. So I drop that video in the chat and start sending it, and maybe I wasn't careful about my settings, so it's 500 megabytes or something gigantic. But that's okay, we can just let it transfer in the background, right, while we keep chatting. So what I'm going to say is when we hit line 5000, we're going to send a file. In this case, it's 512 megabytes. So that'll happen partway through the chat. So over here, we had some chats, but now we're waiting for the file to send, and no more messages are getting through. So TCP has a problem referred to as head-of-line blocking. So essentially, because each byte must be in order, messages are not allowed to jump the line, even if the application would want them to. So in this case, when I go to send that file over the TCP socket, that file now, in its entirety, takes up a lot of bytes. And it takes time to send that over the network, because 512 megabytes is over Wi-Fi. I mean, it takes a couple seconds, not outrageous. But during that time, every other message behind it is waiting for that one really big message to get through. So if you're in a web environment, for example, maybe you have to open more than one session so that your head-of-line blocking file transfers don't impact the real-time stuff. And it used to be really common to do this, like File Transfer Protocol FTP, for example, would always open a new socket to send data. But in modern times, we don't like that because firewalls freak out about it. So head-of-line blocking is a real problem for some applications. I mean, this is just a text chat, so we can handle not talking for a few minutes. But if we were in a voice chat, we'd drop the call entirely because all of this background traffic that's not very important, realistically, or not timing critical, is blocking our timing critical smaller traffic because they're part of the same socket. But in the end, we still ended up with all the data correct. We just had to wait longer for it because it's being blocked by the big file transfer. So imagine now I have a real-time application. I'm sending audio or video that's supposed to be in real time. So if I lose a frame of video, for example, on the internet, some packets get lost, is it better for me to wait to resend those packets or just skip the frame entirely and go on to the next one? That's the question a lot of real-time applications have, and it's why they don't like using TCP. So TCP, we must guarantee all the data makes it through. But for real-time applications, if that data is now stale, we would have been better off just getting rid of it entirely. So it's only useful to us for a certain period of time, after which it's gone. So TCP can't provide that. So a lot of real-time applications now are based on UDP and implement their own forms of reliability over UDP. And our friends the OSI enter the story again here. So I'm sure I've talked about the OSI model. You've probably heard in formal classes, etc., about the OSI model. But have you heard about the OSI organization and the OSI protocol suite? So in the late 70s, early 80s, there was a push to modernize the telephone network for data communication. So the engineers from DARPA, the US Department of Defense, they were working on the internetworking protocol, along with their colleagues from Europe in various countries there, and they were making great progress in internetworking. However, the phone companies had a very different idea of how data communication should go. You see, they were charging for telephone calls by the minute. And so they thought that data should be charged either by the minute also, or by the byte. And so you would pay for connections to the telephone network. Back then also, every single phone line was going to the telephone company. So private branch exchanges weren't really a thing yet. So if you had 100 phones in your office, you had 100 phone lines going to the phone company, they would manage those subset of numbers for you, etc. They imagined the same thing for data. If you had 100 computers on desks, You would buy 100 X25 circuits to the phone company. They would provision them all up with their OSI network addresses at the network layer. You could buy different tiers of network service, reliable, unreliable, etc. X25 was the one that I've heard come up the most, which I believe was a reliable data transport at the network layer. And so then based on that, you were managing the transport layer yourself, and the network layer came from the phone company. So the transport layer was now your interface between your applications and your network provided by the phone company. So it had to do multiplexing. But if you paid for reliable service from the phone company, you didn't necessarily have to do reliable transfer because the phone company might do that for you. It depended. So the committees of OSI, which is a combination of the ITU, which is also really bad at design by committee, and the ISO, which is also really bad for design committee, they merged forces for the worst committee ever, and they came up with 5 different transport layer protocols, which they thoughtfully called TP0 through TP4. And each of these provided a different set of guarantees. Some of them also provided multiplexing, some of them provided in-order delivery, etc. But they were all different, and applications could choose which of them they wanted to use or support. And of course, since there's 5 of them, some applications would support different similar ones, like 0 and 2, or 4 and 2, or whatever. It was a mess. So this whole disaster went on to become frame relay, and deeply embedded itself in the telephone network in the late 80s as ISDN. And by the late 90s, it was abundantly clear that this was the wrong choice. So the whole legacy telephone network had to transition the other way to the Internet Protocol because the Internet Protocol had clearly won. And so a group of engineers designed a new transport protocol for the Internet to carry all of this old signaling traffic from the telephone network. They used to be carried over TDM, frame relay, ATM. And they called this the Stream Control Transmission Protocol, and it's broadly part of SIGTRAN. So in SCTP, we have port numbers like we do in TCP and UDP. We have IP addresses underneath us at the network layer. We are doing connection multiplexing. We're doing a stateful connection that we've established between 2 peers. And across that, we have the choice of what we can send. So first off, to resolve the head of line blocking issue, we can have multiple streams identified by stream number. And each stream guarantees ordering only within the same stream, and some amount of sharing across the streams happens. So we can dump files on secondary streams and not worry about polluting our real-time data stream or something like that. We also can guarantee message boundaries if we would like. We can choose how long a message is valid, and if it exceeds that time, it gets dropped. And the application has full control over this at the SCTP socket level. So I've rewritten my chat program to use SCTP, and let's take a look at how that works. So in theory, SCTP can provide us with all the guarantees we got from TCP plus some. So it always does connection multiplexing, so we have port numbers. We can identify a specific application on the host. It also always provides us a connection-oriented approach. So unlike UDP where we never make a connection, we're always establishing a connection in SCTP between the 2 endpoints, whether or not we're using packet mode or stream mode. It provides us reliable in-order transmission, retransmits, etc. It also provides us with message boundaries, so we can read one whole message if we would like. It also has one other neat trick, and that's that it can multipath. So if we have multiple addresses on each host, SCTP can be aware of all of them and send packets using all of them. Possibly for reliability, we could send the packets down both paths, possibly for improved bandwidth, things like that. So multipath TCP can do that in theory, but is not widely rolled out, but SCTP can do it natively. It's actually also drop-in compatible, so if I take my TCP demo here, and I find the line where I actually configure TCP, so IP proto TCP, I can change that to SCTP and recompile, and it should just work like this. So I just rebuild that, and then TCP. So this is actually going to use SCTP now. Let's go ahead. And we'll do our send again. And we're getting hung up by the head of line blocking again, because we still are doing in-order delivery, but seems to be working fine. So SCTP supports both stream-based, which is byte by byte like TCP, and also message-based like UDP, and sort of a mix of the two of them on the API side. So in UDP, we always start with a socket that gives us a file descriptor to read and write to. We then bind that socket to a local address and a local port number, and then we can send and receive messages in that socket, which are destined for sent from that address. With TCP, we have a connection-oriented approach. So we start with socket again to get a socket. We bind that again to a local IP address and local port. We then do a connect, which is where we're sending out a connection, or we do a listen followed by an accept, which is where we receive a connection, and then we can read or write on that connection object. So reading and writing is just bytes like any other read or write object. So in SCTP, we sort of have a mix of the two. So we can do exactly what we did in TCP and it will work. And that's the sort of backwards compatibility for TCP. But we can also do sort of like UDP that'll work also. So we can do bind, socket, or socket bind. Then we can do connect, but no listen and no accept, because we can still accept multiple connections on the same socket, unlike TCP. And then we can read message, write message, like we would in UDP. Or we can read and write onto a stream like we would in TCP, and all of that is valid in SCTP. And if we use send message, receive message, we have additional options to control how long that message is valid, what stream it uses, things like that. So of course we had no issues here using SCTP, but we still suffered from the same head of line blocking problem. So just to prove we actually are using SCTP, I'm going to run SS, which shows socket stats. We're going to look for TCP, UDP, and SCTP, and just listening sockets. So in this case we have all of these listening sockets for UDP, TCP, and we got one down here for SCTP, that is my TCP receiver. But of course, I wrote a full SCTP example as well. And so in this one, we send the files in a separate thread using a separate stream. We're using sequential packet mode, which is the sort of UDP-like. And we're using send message, where we can now use a stream number, time to live, and other things like that. So I'll again start up the receiver. And here we go. So we got all of our messages pretty quickly, but we're still sending that file in the background. So again, we were 100% successful, no reordering happened, and now any day now that file transfer should complete, and then it should pop up with a message down here. So I used a different stream in SCTP for the file transfer, so it didn't impact my message delivery. It could have some impact because there's not a guaranteed separation of streams, but essentially the kernel will pick from the streams relatively equally when it's sending data, in theory. And there we go, transfer complete for stream 1, and we got notification messages, which is fine. Oh yeah, SCTP also formally notifies you of connection events, like the connection being dropped, etc. So if you're doing multipath, for example, there's a formal API for how to deal with that at the application layer. So what ended up happening to the magical stream control transmission protocol, and why isn't it everywhere today? And essentially there's two answers to that. The first answer is network address translation killed it, so thanks IPv4. And the second answer is it's still alive and well. So I'm sure many of you have heard of IP version 4 addresses. They look something like this. And back in 1991, the IETF, who develops the Internet Protocol, they realized that if the Internet were to take off beyond the research organizations that were running it at the time, they would not have enough addresses in only 4 digits to uniquely identify every system on the internet. And that was very important because transport layer multiplexing is within a host. So we can't use TCP UDP, at least not 1991, to multiplex different systems. So they set out to seek comment on the next generation internet protocol, IPNG. In 1994, they selected the new choice. It was called the Simple Internet Protocol, SIP, and used the version number 6. So it got turned into IP version 6. They started running test networks shortly after that. They built a global test network called 6Bone starting in 1996. And by 1998, they had fully fleshed out the new protocol and released it. And unfortunately for them, between 1991 and 1998, the internet grew up like that. So now over the course of just a couple of years, while the IETF was busy solving the problem and almost finished, the IP version 4 suddenly became deeply embedded in tons of new businesses. The dot-com boom was growing. Everyone wanted to run a website. Everything that existed ever was being put on the internet, however poorly that turned out for them. And so now IP version 4 was in a pretty big pickle. So as designed, it could not scale this far. The first thing they did was classless interdomain routing, CIDR, which also was part of the IP version 6 protocol that got backported to IPv4. And so with CIDR, they could use more variable subnet masks. And that was the start of a good thing, I guess. But the real thing that made the internet viable without running out of addresses in 1998 was network address translation, and especially network address and port translation. So in network address and port translation, we recognize that the 32-bit address is not enough to uniquely identify every host. So they kind of looked sideways and they're like, TCP has 16 more bits, and most of the time you're only using a couple of them. So what if we robbed a bunch of bits from TCP and pretended like they were part of the IP address? And that's kind of sort of what network address translation does. It's robbing bits from the transport layer to extend the network layer address. And that worked okay for TCP, that worked okay for UDP too, but then SCTP came along, and it also uses 16-bit transport addresses, so we could rob some of its bits as well, but it also uses a much stronger checksum, because as the internet had grown, SCTP realized that the internet checksum from 1977 or whenever they developed it was a pretty shit checksum, so it used the new Ethernet CRC. It actually uses the Castagnoli version instead, so it uses a good checksum, and that means we can't just change the port numbers and leave the rest of the packet the same. We actually have to recalculate the checksum. That's a lot of work. The other thing is that SCTP now supports multi-homing natively, and if we are going to mangle its port addresses, we also have to look deeper into the packet and mangle all of those other transport addresses, and that's also a lot of work for NAT. So there was never a standardized method of how to network address translate SCTP, at least not for port translation. And so anyone running IP version 4 with network address translation could not get SCTP through the NAT. You could use it on your own local network, you could use it on the internet, but you couldn't bridge those two together. So for the phone companies, they were transitioning from frame relay and ATM to SIGTRAN over IP and SCTP. That was fine for them. They could dedicate a whole IP address, IP version 6 address probably, to every single host in the phone network on their own internal network and never have it leave the internet. And that was great. And so some of the other users of SCTP became very fond of it. So the mobile phone industry, for example, they were using GSM over bare TDM lines at T1E1. They went to bare ATM, so they're not using OSI, they're just using ATM directly. They migrated for LTE from all of that to SCTP. So now in modern 4G LTE, modern 5G, all of the control signaling uses SCTP. Between the towers, the mobile switching centers, databases, all of that communication across the core network and the edge network is all done over SCTP for the control plane and UDP for user data. And that works amazingly well because they don't have to deal with NAT. And so in those niche applications where NAT was not a factor, SCP really did take off. And there were a couple of other protocols that got roped into this. So Diameter was developed by SIGTRAN to replace Radius. It runs over SCTP instead of UDP. SIP, which is the voice over IP protocol, it got rolled into LTE as voice over LTE, and they upgraded it from UDP to SCTP for that purpose, and it works really well there. But again, because of NAT and to a lesser extent firewalls, SCTP couldn't travel across the internet and thus didn't get adopted. But it actually did get adopted in one other niche use case, and that's WebRTC. So if you've ever done like a Microsoft Teams call, Zoom, that kind of stuff, they're using WebRTC to peer-to-peer connect different viewers, stitch together video streams, audio streams, stuff like that. And WebRTC is not based on SCTP, it's based on UDP. It's actually based on datagram TLS or DTLS. And within DTLS, they encapsulate multiple streams, which can be video, audio, or SCTP. And they use SCTP for all of the control signaling and the ancillary data signaling that's not the live video and audio. And that is actually at the application layer running inside of DTLS, inside of UDP. And the other place that the wisdom of SCTP came out was in QUIC. So you may have heard of QUIC. So QUIC, I don't think it has an acronym, but it's essentially a multiplexing transport layer protocol that includes encryption, but is entirely in the application layer. So because of all of the challenges of using TCP for web browsing, the web browsing people were very upset about head-of-line blocking. If you load a bunch of web pages over the same connection, you're waiting for them one after another, when you could be sending them all in parallel. Every time they come up with a new congestion control algorithm, you have to wait for Linux to implement it, Windows to implement it. And so they wanted their own better transport protocol, and they couldn't use SCTP because it was going to be blocked by firewalls and NAT. So they had to use UDP and build it all again from scratch in user space. And that's what QUIC is. So it has many of the similar design ideas to SCTP. We have multiple data streams so that blocking is not on the whole connection, it's per stream. We now get transport encryption, TLS, as part of the connection setup process. And that is what QUIC is today. So it's essentially the modern stream control transmission protocol. Now, if you're interested in running any of my demos, you can find them on my GitHub, link here, link down there, something like that. They're all written in pure C. They're each a single file, really easy to compile. Now, I only tested them on Linux. And on Linux, you might need to install libsctp-dev to get the SCTP headers. Now, SCTP is in the kernel on Linux and is very well supported there because it's used by the telecom industry. However, it might not be compiled by your distro because it's optional. So I found some cloud images don't include SCTP support, but the full desktop images seem to always have it. So it's not that rare. If you're on another operating system, BSD also has excellent support. Windows and Mac, not so much. I get the feeling that the telecom industry is not basing their whole core network on Windows very much. BSD and Linux, though, those guys are doing pretty well. Also, if you want to buy my merch from me, merch store, link down in the description below. Free shipping to everyone in the US on my merch. It's a great way to support my channel. If you want to chat with me more, feel free to argue in the comments section about your favorite transport layer protocol. I also have a Discord server, link down below for that. I'd love to chat with you guys there, and I will see you guys on the next adventure.